This is the second of two lessons on the Flight Management System, or FMS. The previous lesson covered components and hardware, whilst this one concentrates on equipment operation. There are about 30 or 40 pages available in the CDU display, depending on the model. Once the system has been initialized, these pages can be accessed either by the function and mode keys on the keypad, or by the line select keys available on the previous page. In this example, taken from one of the climb pages, the page allows you to select maximum rate of climb, maximum angle of climb, one engine out climb, or required time of arrival. However, the startup sequence always follows the same 4 pages, which are the identification page, the position initialization page, the route page, and the performance initialization page. You are not required to know how to use the CDU in this kind of detail for the exam, but we'll go through these pages to give you practical examples of how the pilot interacts with the FMC through the CDU. This is the ident page. The pilot should check that the aircraft model and engine rating in the FMC corresponds to the actual aircraft being flown. This may seem too basic to be necessary, but you should remember that all the Boeing FMCs have a strong family resemblance. It is possible for them to be put in the wrong aircraft or wrongly programmed, especially if the airline operates a mixed fleet. The same applies to the family of Airbus FMCs. Next, the start and finish periods of the nav database AirRack cycle should be checked. In fact, if they are out of date, an alert message will be displayed. If the operational program and the latest software update are known, they can be checked too. On conclusion, the POS init line select key is pressed to move on to the next page. This is the position initialization page. The IRS has a non-volatile memory, and so will remember its last position before the previous shutdown. This is shown here. The airport, which is Amsterdam, or Echo Hotel Alpha Mike in this case, will also be remembered. The airport reference datum will be shown. If it is not already present or needs to be changed, the pilot can overwrite it. The latitude and longitude is held in the nav database and does not need to be entered. Similarly, it is sufficient to enter the parking bay, gate Delta 16 in this example, for the latitude and longitude to appear. The pilot accepts or re-enters the initial position to commence IRS alignment. It is possible to select different time zones on many systems, but usually unnecessary. All flying operations are conducted in Coordinated Universal Time, which, for all practical purposes, is the same as GMT. Local times are not generally used in aviation. On conclusion, the route line select key is pressed to move on to the next page. The route page starts with the departure and destination airports. In this example, they are Amsterdam Schiphol and Liverpool John Lennon Airport. It is usually sufficient to simply enter the company route number. In this example, flight number 602 is the company's route from Amsterdam to Liverpool. And it is a repetitive flight plan. The pilots should know which runway is in use by the time they program the FMC. If the company route is not already programmed, the route can be entered using the VIA and TO columns. This page offers us only one option: performance initialization. Here is the performance initialization page. The gross weight in metric tons in this example is taken from the dispatcher's trim sheet. The desired cruise altitudes are entered. The planned fuel from the trim sheet is entered. This is compared with the actual fuel gauge measurement, which is directly connected to the FMS. If there is a discrepancy larger than a specified limit, a warning will be given. The zero fuel weight is entered. This is added to the fuel figure. The answer should be the gross weight. If it is not, again, a warning is given. The forecast wind, ISA deviation and static air temperature are entered to allow the FMS to plan an estimated flight time and fuel burn. In flight, as actual data is gathered, these estimates will be continuously modified. The cost index is entered. This figure modifies the target cruising speed in order to balance the fuel costs and maintenance costs of the flight in the most economical way. This will be explained shortly. As before, there is only one page we can go to. The N1 limit can be set to reduce engine wear in the climb. Let's explain cost index. We'll use a worked example. Suppose we have an aircraft that can be flown at either high-speed cruise or long-range cruise. Let's say that over a particular route, high-speed cruise takes 3 hours and long-range cruise takes 3 hours and 10 minutes, but uses less fuel. Your job as an airline pilot is to operate the aircraft for your company as economically as possible. Which do you choose? You might think that the answer is obvious. You would select long-range cruise. But it's not as simple as that. There are other operating costs. Let's now suppose that the aircraft has to go in for planned maintenance every 1,000 hours, and it is then out of service for a week. In that time, not only is the airline paying for maintenance, but the aircraft is out of action, not generating revenue. These figures, by the way, are simply illustrations. They are not necessarily based on any particular aircraft. Let's say that if we fly at high-speed cruise, we can make 300 revenue-earning flights between maintenance. We'll allow 100 hours for positioning flights and crew training. However, if we fly to save fuel, each flight is longer and we can only get 284 revenue-earning flights in the same maintenance interval. This is a difference of 16 flights, each of which might have 100 passengers on board. We have lost up to 1,600 fares between maintenance intervals in order to save some fuel. Is it worth it? The answer is that it depends on the relative cost of fuel and cost of maintenance over the route that the aircraft is operating, and these will be different in different parts of the world. However, for each route, they can be calculated by the operator's cost accountants. There will be an optimum point which, for any particular route, is the most economical speed to fly. Cost index attempts to quantify this. It is determined by dividing aircraft operating costs by fuel costs. Only those portions of operating costs affected by trip time are included in the calculation. The range of values is then put on a sliding scale, which is from 0 to 200 for the Boeing Classic series of FMCs. If 0 is selected, the FMC gives maximum range airspeed and minimum trip fuel with a low speed descent. If 200 is selected, the FMC gives VMO or MMO for climb and cruise and a high speed descent. The company will specify a cost index to be used for each route. A required time of arrival mode is available in order to arrive on time at some designated waypoint, such as the final approach fix, holding fix, or airport. The FMC computes a recommended takeoff time, then gives target speeds to fly, and continuously adjusts them in flight. Speeds are automatically corrected for in-flight winds and route changes by adjusting the cost index. If RTA mode is used, taking off late will add to the cost, as the aircraft will have to fly faster.